Welcome to this talk on using deep learning and customized Solr components to improve search relevancy at Target. Um, so a little bit about Target. So we have over 1,850 stores and still growing. And we have an online business at target.com. There are many different ways to shop at Target these days. You have same-day delivery. You have the 2-day free shipping, and you have things like scheduled delivery and order pickup and so on. We have global offices in China, Hong Kong, and India, and many other places as well. Um, a bit about us. I'm Sunil. So I work on the platform side of things, enabling ranking and relevancy. And then there's Ashish, who works on the Solr side of things. He develops custom components for us. And Richard, who's a data scientist and our deep learning expert. We'd be happy to connect after the talk and also probably take in the questions at the end of the talk. So this is the agenda that we have for today. So we're going to probably talk about, how we've used Solr at Target, just a brief architectural overview, and then some of the Solr components that we have developed, and some of the deep learning techniques that we use for developing our classifiers. So before that, I would kind of try to understand by having a show of hands on how many of you kind of use a homegrown version of Solr here. So, okay. So that's about like 30%. How many of you have kind of developed custom components within Solr? Oh, that's a good number. And how many of you have developed classifiers and possibly used classifiers within your systems? Okay, cool. So this is our journey at Target. So we moved away from Solr. We moved away rather from a proprietary engine about 5 years back. And coincidentally, this is the 5th year that we've been presenting at Activate and Solr conference. We have a growing index. We have about 2 million SKUs right now, and that's kind of growing. We run a highly performant engine. So our P95 is about 250 milliseconds, and our P99 is less than 450 milliseconds. So, and we do a lot of stuff within Solr. So even with that, we kind of run a highly performant engine. And we've customized our Solr not just for relevancy. We also have something like store availability. So some of the things that I talked about in terms of shipped or even 2-day shipping. So a lot of those things are actually driven via Solr. So this is kind of an architectural overview of it. So if you could see this could be kind of broken up into 3 major parts. One is the query aggregation part, which is the query processing part, I would say. And then there's the Solr part, and then there's the indexing part over here. So if you typically look at it, it would be like a query flowing into platform services. And the platform services basically calls a bunch of other dependent services that it requires, and also calls the relevancy engine. So the relevancy engine is basically some kind of an aggregator that we have, which would essentially call different classifiers, so to say. So you could think of the classifiers as to be an item type classifier, or a brand classifier, or a color classifier, and so on. So you could have n number of classifiers there, and it basically calls this and gets the signals from the classifiers and aggregates it and kind of gives it to the platform services. And the platform services kind of aggregates everything from the other services as well, and forms a Solr query essentially. So there could be other parameters that could come in for store availability, for example, and it aggregates everything and then calls Solr. And the Solr also calls in a key value store that you would see there. That we kind of use for our store availability. And essentially that kind of forms the overall architecture point of view. So there are a couple of things that we do on the data pipelining side, just as we kind of not just put in the data that we get from the source, we also do some kind of augmentation and normalization of the data. So you wouldn't want to just put it as it is. So there's indexing, there's pre-processing of the stuff, pre-processing of the source, and we kind of index it into Solr after that. On querying the Solr itself, these are so we use Edis Max as our query parser, and there are a bunch of attributes that we would kind of query on. So these are some of the examples. So the attributes could be based on title, for example. So that's the example. There is women's sling backpack. That's the title that we get. There's a category. So the category is basically the taxonomy or the hierarchy on which the item belongs to. For instance, this one belongs to women's accessories, handbags, and fashion backpacks. And then there's an item type associated with it. In this case, it's backpack. And then there's this description of what the item description is. So as I kind of mentioned on the augmented and the normalized data, so we kind of augment and change the data that we get or the source that we get into something like that. So we might change feet to feet, the inch to inch, IN to inch, and inch, the symbol inch to inch, and so on. So when we are kind of querying Solr, the recall and the precision is controlled by various factors. So it could be a combination of these different factors that we use. So there's a category attribution classification. So for example, the student desk belongs to the desk category or the queue hierarchy. So that means that once we get the classifier to give us this hierarchy, we use something like a BQ parameter within Solr to boost those boost those items which belong to that category's queue hierarchy. Similarly, we also use filtering-based techniques, which is basically FQ and Solr. So if the student desk belongs to desk, hard stops, and kids desk categories, we want to show items which are only within that category, within that item hierarchy, rather than everything else. So this kind of helps us in restricting the recall, as well as when people do a sort by, say, price or high to low or low to high, you don't show them things which are not belonging to that category or hierarchy. We do use a customized component which is based on Elevate component in Solr. So what we do is, there are a bunch of things that we could do in here. One is, it could be a query to skew Elevate, which is you have a query and you have a bunch of TSINs that you want to promote it to the top. So you can do that. Or you could also do it in terms of attributes. So if I have an item type that I want to boost it, I could do that as well. And we have something called as the precision component, which is, so we want to control on how many basically the items which fall below a threshold of scores, we want to cut them off from the result set. So we have a custom component which is based on a post filter, where we cut or remove items or filter out items based on the threshold. So so Ashish, who is one of the co-presenters here, would talk about the various Solr components that we have and dive deep into them. Yep. Thank you.
Hey, everyone. So I'm actually going to do a bit of a deep dive into a bunch of custom Solr components that we've developed in-house at Target. So the the main goal was to basically enhance Solr's functionality, so that we can control our precision and recall in a more fine-grained pattern. So, so I want to talk specifically about three main components that we've developed in house. The first one is something called a precision control component. So, this is basically um, to restrict the recall set in such a way as to ensure that our precision is very high. The other is something called a score combination function. So this is basically implemented as a post filter. And what it does is it combines various signals from various different sources. I'll talk about all the signals and how it does the combination in a bit. And the third one is how we've overridden the elevate components functionality that comes pre-packaged in Solr. So let me go on to what the precision control component does. So if you look at the graph on the right side of this chart, it basically maps the score distribution for various documents for a typical query. As you can see, this graph shows a bit of a long tail in the score distribution, and this is kind of the pattern that we see for a large majority of our queries, where there are a few relevant documents, but then beyond a certain point, the doc scores sort of start tapering off, and there's like a long tail. And what we want to do is we want to be able to intelligently filter out, or rather put a threshold, a score threshold, in such a way that only we retain the most relevant documents. And the various ways to do this, the simplest you could do is to just take like a percentage cutoff on the top scoring document. So you say that, hey, I want to only keep documents that are within 40% of the top score. You could do something a little more intelligent. You could look at the statistical distribution of the scores and try to come up with a point where, like almost like an inflection point. So there are two aspects here. One is to determine how you're going to come up with the score threshold, and the other is actually implementing it and filtering out documents that don't meet this threshold. The problem here is that you need to do two passes to get this. The first pass is to actually determine the score distribution, and the second one is to, again, go over the documents and filter out the ones that don't satisfy the threshold. In the beginning, we were actually firing two different Solr queries, one for getting the score distribution, and the second to do filtering. But clearly, that turned out to be super inefficient for us. So we had to look at other solutions, and we kind of took inspiration from the implementation of the collapse component in Solr, for those of you who are familiar with it. The high-level idea is that we've used something called, we've extended a post filter API. A post filter typically has a collector that exposes two methods in its API, the collect and the finish methods. The collect method is basically the one where most filters just return a Boolean value, a true or false, saying whether a document has passed this filter or not. And then there's a finish method that's just used for doing like a bunch of cleanup, a bunch of cleanup code. What we've actually done is we've kind of hacked in a little bit. And so what we do is we do the first pass in the collect method, and the second pass, which is the actual filtering pass, in the finish method. Let me just show you a small code snippet of how exactly we're achieving that. So on the left panel, what you see is the collect method where we do the first pass. So in this case, I've just written a simple max score, like the statistic we are collecting is just the maximum of all the scores of the documents in the result set. Whereas in the second pass is on the second panel, which is the finish method, and we're only retaining those documents in the candidate set that pass a certain max score threshold. Here I'm taking 40% off the max score. So that's basically how we've achieved precision control using post filters. Moving on to the second component. The second component is what we call a combination function. So the combination function aims to blend scores of various different attributes. To give you an example, Let's say for a given query, you have a classifier that tells you, hey, these are the top 3 categories that I'm super confident about for this query. Similarly, like these are the top 3 brands that I'm super confident about for this query for a typical e-commerce catalog. You could have a bunch of different other attributes as well, like popularity of a certain document and so on. And the sort of the holy grail here is how you're going to combine all of these scores into one final document score that gives you like a concise value for how important this document or how relevant this document is for the query. So the various ways you could combine scores, you could just take like a linear weighted combination or a polynomial combination. You could do something a little more complex, like a step function where for, let's say, the top 100 documents, you're applying a certain function and then you're applying a certain other function for different tiers and so on. So let me actually move on to exactly what kind of signals and what kind of scores we want to blend. One example, like I said, is like a brand or a category that you're super sure of. So let's say a brand, Goodfellow or whatever. The other, so you would look this up basically in your reverse index. So you do a reverse index lookup for the brand Goodfellow, basically what a typical FQ filter does. Similarly, you could have a top selling SKU for a given query, which is again very query dependent. You know that for a query, a certain SKU is top selling, so you want to be able to boost that SKU. So again, you do a reverse index lookup for that. But you could also have a query independent boost. Like for instance, you know that here there's a certain SKU that independent of the query is like really selling well, and you want to be able to boost that to the top based on a score threshold. And for that, you could do like a forward index lookup. Forward index is basically your doc values. So these are basically your different signal sources and how you get the values for these signals, the boost values for these signals. And the place where you actually combine these scores, we're currently looking at combining these in the post filter itself, where we are doing our precision filtering. There are different places where you could be doing this using a custom scorer and so on. But for now, we felt like post filter was like the best API for us to implement this in. Moving on, the third component that we have overridden is the Elevate component. A bunch of you must be familiar with what the Elevate component does. It takes a bunch of results and forces it to the top of the ranking order for the result set. So basically, this takes precedence over all other sorts, like sort and score, sort and price, etc. So just to give you an example, let's say you search for shoes, and you're very confident that a bunch of Nike shoes is top selling, and you want to be able to show those specific SKUs on the top. You can just do what we call as an elevate. So you just put them in like a static XML file that says that for the query shoes, I want to see these 3 SKUs on the top. So this also sort of is a bit of a limitation of the current Elevate component, which is that you're expected to give this query to SKU mapping in a static XML file. It doesn't allow you to read this sort of ranking from different sources. So I'll come to how we've sort of worked around these limitations. But for those of you who are not familiar with what the Elevate component actually does, so basically, Elevate component is nothing but just another sort profile in the multi-sort functionality in Solr. So let's say you the default sort is on score, but let's say you also wish to sort on price. So first on price and then on score. But let's also say that you want to be able to elevate a bunch of documents to the top. So what you also have is an elevate rank. So the higher the value, the more confident you are of that document. So as you can see in this case, it's basically just a multi-sort or lexicographic sort that you have in all spreadsheet software. So you first sort based on the first column, and then if 2 documents have the same rank based on the first column, you disambiguate that sort using the second column, and so on. So this is basically how Solr does multi-sort, and this is basically how the Elevate functionality fits into the broader framework of sorting in Solr. So let me just quickly come to what customizations we've done to the Elevate component. One thing that we have customized is that you can bury SKUs to the bottom of the result set. So let's say there are a bunch of SKUs that you're sure are out of stock or they're not selling or whatever. You want to be able to bury them to the bottom of the result set. That's a functionality we've added on top of current Elevate. We've also modified it a little bit to be able to send the SKUs that you want to elevate via URL parameters rather than reading it out of a static XML file. So this just gives you a little bit more flexibility. And it's also possible for you to read the signals, the elevated signals from doc values, like if you want to do a forward lookup on store availability and so on. So these are some of the features that we have customized. There's a few more we're looking at as well. But at this point, I'll actually hand over to Richard, who'll be walking you through how we're using classifiers and deep learning to come up with various brand and category signals. So over to Richard.
Thanks, Ashish. I'm going to briefly talk about how we do the query understanding part of the search. So the objective here is to accurately and fully understand user intent in terms of the product attributes based on the input search query. For example, if this query is C9 running shoes for boys, we want to be able to understand that the brand is C9 champion, gender is male, the category is athletic shoes, sneakers, age group is kids, toddler, junior, material, and so on and so forth. So we treat this as a classification problem, and we design a classification framework that for each product attribute automatically generates a model to classify any query into that attribute. So just a quick overview of the classification framework. First, we gather a lot of training data. The most important two data that we use is the user search to behavior data. That includes user clicks, add to cart, purchase, etc. The second data is the product attribute data that includes SKUs to category, SKU to color and size, brands, gender. So these are all attributes of a product. And then the second step, we train machine learning models on a per attribute level. And the training data consists of a list of query and attribute value pairs. For example, let's say for the category attribute, the training data will look like shoes and associated with athletic shoes, and the shoes associated with sneakers, etc. During prediction and serving time, when the input comes in, like for example, student desk, the output of this classifier is going to be a list of predicted attribute values, such as desk, kids desk, hutch top, and each with a probability, and that are then passed to Solr through the BQ, FQ, and the custom parameter. So let's quickly go over the pipeline. During the preparation step, we basically have the attribute extractor that extract all the SKU to attribute value pairs from the product catalog. And then we have the query attribute aggregator that aggregates this the query to those attribute values using this search and click stream data. And that gives it the query to attribute value training data that will be then used for the training through our n-gram convolution neural network. And that gives us the query classification model. During the prediction, which is the serving time, when given a user input query, we'll pass it through the model, and that will give us a list of predicted attribute values. For the training data preparation step, as I mentioned, we use the user behavior with the clickstream data and the product attribute data. So the first thing is the search query to product SKUs, clicked or add to cart or purchased. And the second is the product SKU to product attribute values. Combining the first and second data above, we can get a search query to a list of attribute values, each with the score. And the score is computed as the number of times attribute value is clicked, add to cart, purchased, given the search query queue, divided by the total number of times that the queue occurs in the entire clickstream data. So for the category attribute and for the query running shoes, in the training data, we'll have athletic shoes with a 0.5 of score, sneakers with 0.2, and sandals with 0.01, which is a very low score, and it will get filtered at the end of the preparation step. This is a simplified version of the neural model that we use. This is for illustration purpose. So given a query, for example, room essentials full-size bedding sheet set, every word has its word embedding. So we have 7 words, so it would be the 7 times 5 input matrix. Oops, sorry. And then through the n-gram convolution, meaning that we have an n-gram window that shifts through the input sentence. During every step of shifting, it will generate n-gram embedding. And then for that n-gram embedding, we have filters that then learn all the weights for that embedding, and the filter size in this illustration is 2. Then passing that through an activation function, we use relu. We will get a feature map for each of the n-gram. So we pass this feature map through a max pooling layer, and then through a drop-up layer, and finally through a softmax layer that will generate some attribute value predictions. So in this example, we have only 2, but in the real example, it can vary from 10 to thousands. And these are the hyperparameters we use. So I'm going to present some evaluation results. Before that, let me define first what the precision recall is in these results. So the precision of a query is the number of correct predicted attribute values divided over total number of predictions for that query from the classifier. That means the higher the precision, the more accurate the predictions are. Recall of a query is the number of correct predicted attribute values divided over total number of attribute values there are for that query in the test set. So that means the higher the recall, the more coverage of those attribute values in the test set for that particular query. The top end accuracy means for a query, if any of the top end predictions is relevant, then it get a scores of 1, otherwise a 0. In the experimental settings, we use the category attribute with 1.5 million unique search queries as training data, 12,000 as the development or the validation set, 12,000 for the test set, and we have around 4,000 predictions, classes we need to predict. This is the precision recall curve. Just to point out that a lot of the precision recall, as many of you know, that there are trade-offs of each other. So the higher the precision, the lower the recall. So in this, we were able to achieve high precision and high recall. The jackpot that are defined as the jackpot region, which is above 90% precision and above 90% recall. And it took us a while to get to this jackpot. And in terms of the accuracy of at least one correct and top-end prediction results, we were able to get, for top 5 predictions, we get 96% of times, at least one correct attribute value is present in the top 5 prediction. And if you look at top 1, it's almost close to 90%, which is also pretty good. And this shows the F1 score versus the probability thresholds. In case you don't know what F1 score is the harmonic mean between precision and recall. And so the higher the F1 score, the higher the precision and recall. So this shows 2 things. So probability thresholds means that, let's say if it's 0.5, that means in the prediction output of the classifier, we just ignore everything below the probability score of 0.5. So we only evaluate the ones above that. And this graph shows two things. One is that we can achieve the highest F1 score at around 0.2 probability. And another thing is that we try to vary three important hyperparameters, which is the filter size, the maximum number of tokens, and the word embedding size. And we can see that the orange line, which is the highest performance model, it uses the highest value of all these three parameters. So that means the more parameters in a model, the better it performs. But there's a drawback that is because the more parameters, the model gets complicated. So it's very computation intensive. So we had to find the right balance between the computational resources we have and the throughput we need to have. So we spent some time on doing that. So the takeaway from this presentation is that our classifiers can achieve precision recall above 90%, have an accuracy of top 5 prediction above 96%. And with the classification pipeline, a new model can be automatically generated on any attribute within 18 hours. So by using the state-of-the-art neural network techniques in conjunction with the customized Solr components, we have improved our search relevancy by more than 20%. Thank you.
There was a slide where you showed the elevate ranks. I'm just wondering how did you come up with that, the elevate ranks?
Oh, that was a dummy example.
But what is some criteria you would use to come up with elevate ranks?
Oh, okay. Sure. So the question was how do we come up with these elevate ranks? Like what metric do we use to assign ranks for elevated documents? What we use, for instance, internally is some sort of a business popularity. So basically, you look through your clickstream data and see which SKUs are selling the most for a given query. And over time, you aggregate that and see and sort of get a list of top 10 SKUs for each query that is best selling, and you give it an ordering based on the sales or whatever business metric you want to optimize on. So yeah, that's how we get the metric.
Do you also do like the query similarity? Because two users might have different search terms, but they're essentially asking for the same thing.
Yeah, that's a good question. So the question was, do we use query similarity for because two different users could express the same intent in two slightly different ways, and they might have the same buying behavior. So how do you sort of normalize across that? Right now, we don't do that. We only do very basic normalization of these queries. But in the future, the goal is for us to move away to a more CNN-based classifier, like what Richard specified, so that we could look at doing this in a more query-independent way. I'll take a question from you.
You said you saw improvement of about 20%. Could you speak a little bit about what your old model was? What was your old baseline, so we can understand the scope of improvement?
Sure. Do you want to talk about that?
Yeah. So in the old system, we're using naive-based classifiers. And the amount of data that was used in training wasn't that much, and so the power of deep learning is that the more data, the better the quality of the model. And if for naive based or these traditional machine learning methods, sometimes it plateaus at some point after some certain amount of data. We do have human labelers to check for relevancy of the search results. In terms of getting rid of the bias, I think so. A lot of the clicks that users they when they click on, those are really the products they're looking for. So right. Right. So this is an incremental improvement, right? So we have rules that can override what the system would show them. So to make it more, like for example, when we were sharing incorrect results, we have rules to override that to make it show correct results, and that the classifiers will pick that up and will improve itself incrementally.
Sure. The question was, for the precision control component, we have two passes. What's the impact of that on search latency? The impact was basically, so let's compare this against what it would look like if we just did one pass. In the second pass, basically, in the first pass, basically what we're doing is we're collecting some statistics, and in the second pass, we are iterating over our candidate set of documents to filter out the ones that don't meet a score threshold, right? From our experiments and from what we've seen in practice and production, it led to about a 10 to 15% increase in the latency. But sort of the benefit that we got out of having the precision component was way higher than the cost we incurred with the latency increase. So, you can take that.
Well, so we do want to keep the top results, like the ones that people really want to purchase. There are ways to figure out whether or not we're missing some items that should be shown at the top. For example, we have dedicated slots that we will just surface some items that are in the bottom of the list, the result, but that we think that it should be in the top, and we'll just give it a chance to see if it actually trends to the top.
How personalized is the experience? Do you guys use user A is like user B, and they produce or buy similar stuff, and therefore that changes, or is it pretty generic across the board?
Right. So that's right now it's generic, and that's a work in progress.
Dealing with predictive bias, and you have the rules engine, like how large of a team works to kind of balance that out, and how often are they touching stuff like that? Do you have an idea of that?
No idea. Sorry.
What is your process of dealing with model decay?
Sorry, could you repeat again?
How do you update your models and train them?
We train the models every day. Yeah.
Can you describe a little bit more about your training data? So, for example, you mentioned that you were using this search queries. How are you associating that search query to a particular category? Since maybe how are you going to understand the user's intent?
Right. So we use the SKUs as a proxy to bridge the queries to the attributes.
So it's part of the source data, right? So the source data would have some kind of categorization. So based on that is how we kind of eventually come up with a list of categories. I think we've probably run out of time, and we can probably connect with you after this. Yeah, thank you.